Hello everybody and welcome back. We're looking at question 24 on the 7th grade Gauss from 2006. A triangle can be formed having side lengths 4, 5, and 8. It is impossible, however, to construct a triangle with side lengths 4, 5, and 10. These two smaller side lengths, they sort of can't come together, and if you imagine quite wide, they can't quite come together to form the peak. So you just sort of are left with three lines there sort of attached on a hinge system, but you don't get a full triangle. Okay? That's the idea. In fact, maybe I can show you a picture with that. So you can do 8, and you can do sort of a 4 and a 5 here. But as soon as you do 10, it's too wide, because imagine the 4 here and the 5 here. And imagine they're sort of attached by points here, and they swing around until they meet. But the 4, that can sort of swing around in this area. The 5 can swing around in a circle, but these circles don't intersect anymore, so these points will never actually touch one another. That's the idea. Using the side lengths 2, 3, 5, 7, and 11, how many different triangles with exactly 2 equal sides can be formed? Alright, so they're talking about forming triangles, and I've shown you a little picture of that, but the way triangles work is they have to satisfy something called the triangle inequality. So we'll talk a bit about that, and then we'll probably start this question on a fresh sheet of paper. So for any old triangle, we can give names to the sides. Now it looks like C is the biggest, but you don't always know which one's going to be the biggest. So the triangle rule says if you want to make a triangle, you've got to have all pairs of sides add up to more than the third side. Not more than or equal, more than the third side. So for example here, we've got 4 plus 5 is 9, which is bigger than 8, but the problem here is 4 plus 5 is not bigger than 10. Now this is true for all pairs, so you also have A plus C has got to be bigger than B, and B plus C has got to be bigger than A. However, in practice, this is usually only a problem for the biggest one, C, being less than the sum of the other two. Okay? So these are collectively, this is the triangle law, or triangle identity, sometimes it's called, or triangle inequality is probably how most people see it in the literature. So we'll call it the triangle inequality for people who want to Google that. Okay? But if you have these three conditions, you get a triangle. And if you have a triangle, it must satisfy these conditions. Okay? So now let's start the question again. We are specifically being asked about triangles with exactly 2 equal sides. So we're not dealing with an A, B, and a C. We're dealing with isosceles triangles, and they're going to have to look like A, and B. Okay? So what do our triangle inequalities amount to? Well, they'd be A plus A has got to be bigger than B. A plus B has got to be bigger than A. And B plus A has got to be bigger than A. Now, as long as B is not 0, which of course it's silly to have a triangle whose side is 0, and they didn't even give us that option, these two are automatic. Of course, if you add a positive value to A, it's going to be bigger than the A you started with. So really, we only care about 2A being bigger than B. And it's this that we need to satisfy. If we satisfy 2 times if we satisfy that the repeated side length is bigger than B, we're all set. Okay? So now we ask ourselves, okay, we use these side lengths here, how many different triangles can be formed with exactly 2 equal sides? And I was about to start talking about equilateral triangles, but exactly 2 equal sides means you also have to have B not equal to A. So I can't do 2, 2, and 2. That's still a triangle, but it doesn't have exactly 2 equal sides. So we have to be a little careful. What have we got? We've got 2, 3, 5, 7, and 11. And notice some of these are chosen, these aren't sort of random numbers. 2 times 5 is not bigger than 11. 2 times 3 is not bigger than 7. 2 times 2 is not bigger than 5. That sort of thing. So what I'm going to do is, I think the easiest way to approach this one is probably just make a little chart. our possible A value, our possible B value. And we'll just we'll go with some pairs, and then we'll say, you know, is 2A greater than B? So we could have A is 2, and then what could we have? Well, we can't have B as 2. Let's try B as 3. Yep, 4 is greater than 3. How about 2 and 5? Well, no, 4 isn't greater than 5. So that doesn't work. Okay. And we don't really need to check 2 and 7, 2 and 11, that sort of thing. Okay, how about A is 3? Could we get B is 2? Well, yeah, 6 is bigger than 2. Could we have, well, we can't have 3 and 3. How about 3 and 5? Yeah, 6 is bigger than 5. How about 3 and 7? Well, no, 6 isn't bigger than 7. Okay, so we've got a bit of a problem. All right, what about 5? Could 5 be our repeated angle? Or not angle, repeated side? 5 and 2? Well, yeah, 10 is bigger than 2. 5 and 3? Yep, 10 is bigger than 3. How about, well, you can't have 5 and 5. How about 5 and 7? Yep, 10 is bigger than 7. You can't have 5 and 11, though. So far, before we continue, sort of wrap this up, we've got 1, 2, 3, 4, 5, 6. Okay, we have to complete our chart, so we still have to consider 7. Okay, you might notice that this is all going to work until we try a number that's more than double A. Everything else less than everything else less than that will be fine. And so you can make the observation, well, we're doing 1 and then 2 and then 3. You'd probably guess that 4 of these will work here. Well, we'll find out. 7 and 2. Will that work? Well, yeah, 14 is greater than 2. So it's going to be a very narrow-looking triangle. But yeah, it still works. 7 and 3, yep, 14 is bigger than 6. 7 and 5, you bet. Oh, it's not even 6, it's 3. Okay, you can't do 7 and 7 because, again, they said exactly 2 equal sides. Exactly 2. So we'll skip over 7 and 7. How about 7 and 11? Sure. Because 14 is bigger than 11, and we've exhausted all our possibilities there. But we haven't exhausted all possible A's yet. How about 11 and 2, 11 and 3, 11 and 5, 11 and 7? All of these are going to work because they all satisfy the condition we need. 22 is bigger than 7, 22 is bigger than 5, 22 bigger than 3, 22 bigger than 2. I mean, that's going to be an extremely narrow-looking one, 11, 11, and 2. But it still works. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 possible triangles should be our final answer. By the way, before I go back and look for 14 amongst our answers, let's see what would happen if we hadn't read that exactly 2 comment quite precisely. You would have had an extra triangle for 2, 2, 2. You would have had an extra triangle for 3, 3, 3. 5, 5, 5, 7, 7, 7, and 11, 11, 11. So that would be 5 more. They're all equilateral triangles rather than just strictly isosceles. So that would be 5 plus our 14. It would be 19. I wonder if 19 is among the answers. Let's find out. So 14's here. 19, however, suspiciously not on the list. 20 is. But we're not getting anywhere near 20. So 14 is a safe thing to go with, and we actually have the numbers to back it up. So there we go. E14, and that's going to be our final answer. And we've used up the whole page, so let's be kind to our future selves and flip the page already in anticipation of that very last question, question number 25, and I'll see you guys for that one next time. Until then, have a wonderful day.